Okay, very good.
So I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Thomas Fischbacher, who will tell us about computational techniques for finding vacua in supergravity. As I always do, I'll remind you that we're open for questions, but you can in particular put your questions up on the chat, and I will watch that and raise them at appropriate points. And then we'll leave a few minutes at the end for questions and free discussion as well. So with that, please, Thomas.
So thanks for the introduction. I'm Thomas Fischbacher from Google Research in Zurich. It's now already past 8 p.m. over here in Zurich. My workday started quite a while ago, so I'm unfortunately already a little bit tired, but I would like to nevertheless say a few things about new results in supergravity via machine learning technology. Can everybody see my slides?
It's good, yes.
Yeah, okay, very good. So let's jump in straight away. My main thesis is that the infrastructure that was built to power the machine learning revolution deserves a closer look in itself, and it actually allows us to make progress on many technically challenging problems. In a way, you could say that we can thank the gamers for cheap graphics processing units, which are just an amazing tool for research. And likewise, we can thank the machine learning community for open source GPU accelerated tensor arithmetics with fast gradients, which it turns out is useful for quite a lot of research. Now, in this particular talk, I'll focus on supergravity. There will be some pointers towards other applications, but I first would like to discuss the technical infrastructure and the underlying ideas, in particular the underlying ideas behind this, and then move on to discussing quantum field theory and quantum gravity applications of this. So this talk is based on a list of somewhat recent papers that started in 2019 with SO8 supergravity and the magic of machine learning, where we first applied TensorFlow to a supergravity problem. And then a few, so this was a Google research paper with no external collaborators. And then there were a few follow-on papers that exploited these new methods in other contexts. And well, then starting from the numerical insights, also did the corresponding analytic constructions and showed that yes, what we saw numerically really exists. The last one is an outlier here, a single photon image classification. This is also, again, Google research only. I did this with the co-author. I'll come back to this particular one. It's interesting for other reasons. Now, let's focus on TensorFlow. What is TensorFlow? Nominally, it's an open source library built by Google to support machine learning. And it is based, or it provides a computational model that captures many machine learning related designs. So what it gives us is tensor arithmetics plus nonlinear functions on tensors plus backpropagation. Backpropagation basically means fast gradients. TensorFlow has a layered architecture. At the lowest level, we have numerical kernels that provide numerical primitives like matrix vector, multiplication, solving linear systems, that kind of thing. This is implemented in C++, respectively, if we target GPUs, then in CUDA. There is another layer on top of this, which provides a graph representation of a computation. So these graph representations are TensorFlow's internal domain-specific language for numerical computations. In TensorFlow 2, it's mostly hidden, but it still exists. Then at the next level, we have low-level Python primitives to manipulate TensorFlow tensors. Now, quite a few here, when they hear tensor, will think about closed monoidal categories. This is not quite the concept that TensorFlow has as a tensor, of a tensor. A TensorFlow tensor actually is a multi-index array that has extra strings attached to make backpropagation work, to make fast gradients work. We will come to this. Then at the next level, we have Python machine learning primitives, such as deep neural network layers or entire machine learning models. And finally, on top of this, there's another layer. This is partly TFX and not TF. And that layer then is about data processing, about training and serving infrastructure. So things that come up in everyday business when doing machine learning. Now, in this talk, I want to focus on these lower levels, so what I highlighted here. And the claim is that this infrastructure, which normally is hidden underneath the machine learning, is perfectly good to use for other tasks, and we can do many useful things with this. Now, to give a mental model about what these lower levels do, we can see TensorFlow as a domain-specific language for machine learning-related numerics. And what we see here, it fits this pattern of having an object language and then a meta language to manipulate entities in the object language. So this pattern we also see in quite a few other systems. So if we talk about the domain of proof verification, proof assistance, and I suppose this has been covered in this seminar and other talks, and consider specifically Hol or Isabelle as a system, then we have an object language that is theorems and also terms, and a meta language that allows us to synthesize objects in the object language, that is theorems, from more basic theorems. And here for Hol or Isabelle, this meta language is ML dialect. And really ML here means meta language. This is where the name comes from. Popular dialects are SML or OCaml. So OCaml would be the flavor of ML used in the COG proof assistance system. That's one situation where this design shows. Then another domain where we have the same principle is fast 3D rendering. If we are looking at OpenGL, now pre-GL shader language in particular, then we have an object language of display lists. And a display list is a sequence of instructions to render triangles that describe a three-dimensional object. And the meta language with which we are manipulating or setting up this display list is typically something compiled low level like C or C++. Another domain where this pattern turned out to be very powerful is digital circuitry design. So if we want to introduce a new ASIC, application-specific integrated circuit, then one very interesting system is the BlueSpec Verilog high-level hardware definition language. Here, our objects are digital circuits, and the meta language with which we are synthesizing circuits from simpler circuits is, well, basically an extension of Haskell. Now, the Haskell language itself also employs this strategy for one particular task, which is doing I/O. Haskell is a purely mathematical side effect-free language, so we cannot just have a print function, for example, because it's not a mathematical function. And Haskell's approach to I/O now is that the mathematical objects we are working with are plans to do I/O, so a plan to print something or a plan to get input from the user. This is what we have in the I/O monad in Haskell. And then the meta language to synthesize more complicated plans from simpler plans is Haskell itself. Now, for machine learning computations, looking at TensorFlow as a system, the object language here is numerical computation graphs, and the meta language with which we are setting up these graphs and manipulating these graphs is Python. So why would one want to represent numerics as graphs? There's a minor reason for this and also a major reason. The minor reason is that a graphics processing unit, a GPU, is not a general purpose architecture like a CPU, but we still would like to have some language for computations that can be made fast, both on GPU and CPU, and now also on the tensor processing units, TPUs, that Google introduced. You can rent these from us. Now, the major reason, however, why this is a useful approach is, well, that we want to make reverse mode automatic differentiation, also known as sensitivity backpropagation, work. What is this about? So it was first written up in a complete and coherent form in Bert Spielpenning's 1980 PhD thesis. And this work, titled Compiling Fast Partial Derivatives of Functions Given by Algorithms, essentially is about the following theorem. So suppose we have an algorithm F that computes a real valued function of n real parameters in such a way that it doesn't override intermediate results. Then we can always mechanically transform this algorithm to another algorithm, grad F, that computes the gradient of that function F with at most 6 times the computational effort and irrespective of whether that gradient has 10 or 100 or 100 million components. It's always at most 6 times the effort to compute the original function. And furthermore, we even get it to full numerical accuracy, which is something we wouldn't get from finite differencing. Now, thinking about it, we are talking about an algorithm-to-algorithm transform here. And this is basically asking for a domain-specific language for algorithms at that point. Now, you might have heard that before, domain-specific language to describe algorithms. This is essentially what John McCarthy's original intent was for Lisp. Now, the problem is that coming up with a generic implementation of automatic differentiation of such an program transformation that gives you a gradient for a real-world programming language is a lot of effort, because real-world programming languages tend to be fairly complex. They grow in complexity over time. Now, there are a few exceptions, and one of them is, of course, the scheme programming language, which was designed to be minimal. It's just a minimal language core, and then everything else happens in libraries. And actually for scheme, specifically our 6RS scheme, this was achieved about a decade ago by a PhD student of Jeff Sussman, Jeffrey Mark Siskind. And this is known as our 6RS AD. To the best of my knowledge, this is actually about the only complete implementation. Well, Haskell has a special role here, but here this was really done for a full programming language. Nevertheless, reverse mode AD, so the ability to get fast gradients, has been commercially relevant for quite a long time. And to give a specific example, if you do, let's say, engine design in engineering, then this leads to numerical optimization problems that can easily have 30 to 300 parameters or so. And it's immensely useful if you have fast and good gradients for that. I'd like to flag up autodiff.org as a website that gives a nice overview over the different automatic differentiation related tools that are widely used in engineering, but most of them have to get creative to solve this problem, that they want to avoid having to build a full compiler. And one technique that is employed by some of these systems is this approach of using a gradient tape. So as we are going through a particular calculation, we are recording all the arithmetic operations that we are going through on a tape. And then when we are computing a gradient, we replay the tape, but backwards. We will see in a moment what this is about. Now, the idea behind the reverse mode AD about doing such an algorithm transform to get a fast gradient in a nutshell is as follows. So you have a function f, and in order to compute the gradient of f at some point x naught, so x naught might be a point in a 1,000-dimensional space. Well, first we compute f of x naught, and we remember each intermediate result. And also when we are taking branches, we remember which path we've taken at the corresponding branches. However, as we reach the end of the computation, we eliminate the return result statement. We do not return that result, but rather we then add further code beyond that point that first looks at the last intermediate quantity that we computed in order to get the result. And we are trying to answer the question, well, at the point where this intermediate quantity was finalized, if I interrupted the computation here and changed this quantity by epsilon, by how much relative to epsilon, to first order in epsilon, would the end result change if I intervened and make the change? This gives us the sensitivity of the end result on that intermediate quantity qk. What we next do is that we look at the next to final intermediate quantity. So in every step, we go back to the next earlier intermediate quantity, qk to qk minus 1. And we answer the same question for the earlier intermediate quantity. And as we go through the entire algorithm that way, as we reach the start, we obtain the sensitivities of the end result on the input parameters. And these are just the entries in the gradient vector. So there are a few small tricks around this approach. One simplifying trick is that whenever a finalized intermediate quantity that is not updated anymore gets used downstream in the calculation, then that particular use contributes to the sensitivity of the end result on that quantity. So if we introduce sensitivity accumulators initialized to 0, right when we introduce these intermediate quantities, we can make backpropagation really a step-by-step procedure as described. Now also, as I explained it so far, it looks as if we would have to do this for every single individual addition and multiplication. But if we have multilinear algebra operations, then we can convince ourselves easily that this backpropagation argument works just as well at the tensor arithmetics level. So bluntly, if we have a final result, let's say that's a scalar product of two vectors, p equals vj, vj, Einstein summation convention understood, then the sensitivity of that scalar product on each of the vj's is well, vj plus vj equals 2vj from left and right derivative of this product. And so product rule. So we can do this at the tensor arithmetic level and don't have to do this for every individual addition and multiplication. Now, generally, we want to run quite a few of these calculations on GPU, and then there is an execution planning problem there, because we would want to put the computation graph in such a way onto the GPU resources that we can do a lot of stuff in parallel. And if we are transforming an algorithm, a particular calculation, into the corresponding calculation of the gradient, it is very useful if we can do the placing of the different operations in the gradient graph independently and take a fresh look at what should be done when and where on the GPU for the gradient to make this really efficient. So overall, this sensitivity backpropagation gives us a third way to think about gradients, in addition to seeing the gradient as a numerical limit or regarding the gradient as a symbolic transform of an algebraic expression, analytic expression typically. And this algorithmic transform has its own characteristics. So I just want to point out here, and this is actually something that I've been exploiting a lot, is that, well, if you think about a symbolic description of a rotation matrix and then think about taking a gradient of an entry of that rotation matrix, then already for Euler angle parameterizations in 3D, this gets somewhat awkward if you do it at the symbolic level. Now, how does this work? This is an actual example that I'm also walking students through when I'm teaching this material at Google. So this nicely illustrates what's happening. However, this example doesn't use any branching. It's really straightforward, straight arithmetics. So to the left, we see a very simple Python function that computes the three-dimensional hypersurface of a four-dimensional box where the side lengths are the four input parameters A, B, C, and D. How do we do this? Well, we first form some intermediate quantities. Well, the first starting with the product A times B and also the product C times D. From this, we then compute the phase 3 volumes ABC, ABD, and so on. And now I'm actually doing this in a slightly more verbose and explicit fashion than I would do this in real code. First summing these 4 different 3 volumes from the 4 different types of sides. This gives me the half area, but three-dimensional area. And then the return value is twice the half 3 volume. And then I'm returning this. Now looking to the right, here we see what we get after doing the transformation that gives us a fast gradient. So the first line after the function documentation string docstring introduces sensitivity accumulators for the input parameters. Then in the following lines, we are just doing the same calculation as before, but as you see, to the right of every intermediate quantity, I'm also introducing such a sensitivity accumulator. Going down through the algorithm, we see this commented out line return red. So as I said, I'm not returning the result here, but rather I'm starting to go again through the calculation in reverse at that point. And I'm doing this slightly more explicitly than I normally would by starting to introduce the sensitivity of the result on the result. And this is, of course, 1. If I adjust the result by epsilon, then the result changes by epsilon. So welcome to the tautology club. Now, this return value is twice the half area. So if I interrupted the forward computation right at the point where I obtained the half area and changed this, incremented this by epsilon, then the result, which is twice the half area, would change by 2 epsilon. So the sensitivity of the final result on this intermediate quantity half area is twice the sensitivity of the result on the result. So it's 2 here. And this is what the next line does. Now, this half area is the sum of 4 contributions. And this tells us that for each of them, if I changed one of them by epsilon, then the end result would change by just as much as the end result would change if I changed half area. So I'm just forwarding the sensitivity here. Then we encounter a line where we see a product. And here's how to think about this. If we know the sensitivity of the end result on the product BCD, and BCD is the product of B and CD, then we see that the sensitivity of the end result on B receives a contribution, which is the sensitivity of the end result on BCD scaled up by the factor CD, which is just a rescaling. And we also have to do it for the other factor. So likewise, the sensitivity of the end result on CD is the sensitivity of the end result on BCD scaled up by the factor B. This is how the product rule here enters in this reverse mode automatic differentiation scheme. And we continue like this, going through the computation. And in the end, we have the sensitivities of the end result on the input parameters A, B, C, and D, and these are just the components of the gradient. If you look at the pre-final line, this is a SP plus equals. So this is a second place where the sensitivity on the parameter B receives a contribution. So we have another such increment of SB early on. I just explained this. This is then the essence of sensitivity backpropagation, and it's actually natural to generalize this to the case where there are loops and other control elements in an algorithm. Now, what we've just seen is that even for a real valued function of 1,000 real parameters, getting a gradient fast and to excellent numerical quality is not a problem. The reason we get this factor 6, it's bounded, is that basically for every step in the forward calculation, we have to do a step in the backward calculation that's the same effort times a small upper bound. So it's never more than 6 times the effort in the forward calculation. And this has a broad range of interesting uses that are neither conventional machine learning nor supergravity. So here are some examples where I've been directly or indirectly involved in. The first one is a recent paper from this year where quantum authors doing quantum field theory took a close look at our SO8 paper and basically learned about this approach, this method, and then adopted it to their problem, which you could see as a lattice quantum field theory problem, instance solution for Schwinger production of 2 Polyakov monopoles. So you can do these things with this technique. Then another thing that was done with this approach from 2012 was working out the spatial structure of well, bound states of solitons in a skirmy model with a skirmion Lagrangian. So a model of baryons up to baryon number 108. In this case, I coached one of the authors, the PhD student on the project, on sensitivity backpropagation and showed them how to do reverse mode automatic differentiation and then use this as a basis for numerical optimization. And the last one listed here, single photon image classification, is a recent paper I did with a colleague from Google Research. And this is, well, one of the main intents behind this work was to provide a kind of Rosetta Stone that discusses a problem that both machine learning and physics people are familiar with, so that they both can easily understand those parts they know about of this work, and then learn about the other half of the problem. And this is especially interesting because it shows how to do problems where you have intermediate quantities that are complex numbers. So it's still real input values, real output values, some complex intermediate quantities. We published the code alongside this work, and this shows how to do such problems. Now, the topic of this seminar is new methods in mathematics. And before I go on to talking about new M-theory results via numerics, I just want to maybe get a bit philosophical. So it's quite common for all of us, as we are doing research, to get stuck on some questions. And often things then get unstuck due to new and better tools. And well, this is also how I would say the general thinking is about Fields medals. So the Fields medal is generally handed out for an amazing new proof technique that's opening doors and allows us to achieve results where we didn't have an idea how to obtain them earlier. Now, of course, what we are doing here is not at Fields medal level, but lately we managed to make some good progress on systematizing the study of some technically challenging problems in M-theory by using TensorFlow numerics. Now, talking about M-theory, there are two big questions about it. The first one is, what is it? So what's its mathematical structure? And the second one then is whether it can explain our universe at all, and if so, how that might work. But the former question is very interesting in itself, and here I'd like to point out that currently we are even struggling to properly define what a quantum field theory is, as is witnessed by this Millennium Prize problem on giving a mathematically convincing definition of Young-Mills theory. So M-theory, as we currently understand it, can perhaps be sketched as follows. In the 70s, it was found that field theories can have fermionic symmetry. So this is what we call supersymmetry. And in 75, it was then seen, and this is a profound insight, that in particular, general relativity can be supersymmetrized. And this gives us supergravity. Overall, there are three possible types of gauge theories that one can come up with. And two of those are observed in nature. One is the gauge theory of vector gauge bosons, so gluons or photons, if you want so. The other one is, well, gauge theory of the graviton, so general relativity. And the third option that exists is having a gauge theory of a spin 3/2 gauge field. And this then is the well, gravitino field. This gives us supergravity. So this then also must contain general relativity, so gravity. Looking at the systematics of supergravity more deeply, one finds that one can play this game in various dimensions and 11 space-time dimensions, so 10 spatial directions and time, plays a particularly prominent role, and we can obtain many other supergravities via, well, typically Kaluza-Klein compactification to lower dimensions, plus perhaps some other tricks. So 11-dimensional supergravity is kind of almost like a mother theory for supergravity here. However, we do know since about 2 decades that per se it's not a viable basis for quantum gravity. It might well be part of the answer, but in itself it cannot work. So the superstring theories, the 5 known superstring theories and supergravities we can see as decoupling low energy limits, so in a way corners of the more general thing that has this preliminary name of M theory. This is the picture that we've had since the second superstring revolution in 95. So we have these different limiting cases that include the 5 superstring theories and 11-dimensional supergravity, and M theory then connects these. Studying M theory, one encounters a few surprises. So in doing this, one keeps running into the same otherwise unusual mathematical structures, in particular the ones that I'm showing in this diagram to the right. The diagram is purely artistic. There's not much of a deeper meaning here. I just didn't want to provide a list because that would have had to put something on the top. And also I wanted to emphasize that really we can go from everything in this diagram to everything else. And mostly what we see here are mathematical objects, the Fano plane, densest sphere packings, clearly the octonions as well, the exceptional Lie groups. Then the passive surfaces, that's perhaps something that really only people with a background in algebraic geometry know much about. Hamming codes, however, that's coding theory. That's perhaps something that computer scientists are a bit more familiar with. But I want to make a point here that the maximal supergravities also fit that picture, and they nicely well belong to that family of closely related mathematical objects, even though mathematics hasn't paid that much attention to maximal supergravities so far overall, I would say. So mostly the relations between these objects are accessible and understood, but some of them are more so than others, and there are still new things to explain and discover about this. Now, 11-dimensional supergravity is uniquely determined by its symmetry properties, well, and also the condition that we only want to have finitely many terms in the Lagrangian, of course. And we can see it as follows. If we take any of the 10-dimensional superstring theories, then by navigating the web of dualities, we can arrive at 2A theory. The strong coupling limit of that, well, actually, if you want so by definition, then gives us M theory. And 11-dimensional supergravity is the low energy limit, if you want so superclassical limit of that. Now, a natural question here is whether the 11-dimensional supergravity equations of motion have equilibrium solutions with, let's say, a large-scale space-time structure where we have, well, time plus 3 more directions that haven't been compactified. And in fact, that works, yes. And in particular, if one takes 11-dimensional supergravity and compactifies it on the surface of an 8-ball, so, well, a 7-sphere, but a particular one, I'm saying it like this because 7 spheres are weird, then this gives us a mostly rigid model in 3+1 dimensions. This is n equals 8 David-Nicolai supergravity, where the gauge group is SO8. In the spectrum, we have 1 graviton, as it should be for a supergravity theory, 8 gravitinos, well, this is n equals 8 after all, 28 photon-like particles, 56 electron-like particles, and also 70 Higgs fields. We can set all the 70 Higgs fields to 0, and this, in fact, is a vacuum of the theory. We have unbroken SO8 gauge symmetry then, and also a negative scalar potential, so this is an anti-de Sitter vacuum, negative cosmological constant. Now, the question is whether there are other vacua of this model, where then the Higgs fields have non-zero value. And here is perhaps a useful reminder that in our physical universe, we do observe a non-zero background value for the Higgs field. This is what gives us electroweak symmetry breaking. Now, in these maximal supergravities, a supersymmetry dictates the specific form that the Higgs potential has to have. And this Higgs potential also then is the Higgs-dependent vacuum energy density, or cosmological constant, if you want so. So this potential is a quadratic function in the fermion-Higgs fermion coupling. So fermion here means either the electron-type particles or the gravitinos. What we want is equilibria of this Higgs potential. And unfortunately, these are in general complicated to analyze. And the complication here comes from the observation that we can see these Higgs fields as providing coordinates on some high-dimensional coset space. And in particular, in 3+1 dimensions, the coset space is the Riemannian symmetric manifold that we get by taking the maximal non-compact, the maximal split form of the exceptional Lie group E7 and modding out the maximal compact subgroup, which is well, SU8 with some part of its center divided out. So if we did it that way, then naively this would ask for something like an Euler-Engel style coordinate parameterization of a high-dimensional Lie group. And well, if you have something like, in this case, 70 angles and your rotation matrices are 56 by 56, that's awkward to do at the analytic level. In 1982-83, Nicholas Warner, then a PhD student of student Hawking, came up with a nice approach here that nevertheless allows one to get partial insight. So we can get quite some useful complexity reduction from a symmetry argument. So if we postulate that we want our residual gauge group, so the unbroken part of the symmetry, to contain at least a SU3 subgroup, then this gives us a 6-parameter problem in 6. So basically, we have a function of 6 trigonometric, respectively hyperbolic angles, and that's doable. And when we have a solution in this parameterization, it lifts up to a solution of the full problem for a simple group theoretic reasoning. So the full 70-parameter problem was considered out of reach for decades, but meanwhile, it basically has been solved, but unfortunately, we don't yet have an exhaustiveness proof. Also more about this later. So here's explicitly how the calculation works for SO8 supergravity, the particular one that we get by Kaluza-Klein reduction on the surface of an 8-ball. So looking at the middle of the expression to the right, we have this VAB. This is the so-called Vielbein, well, the 56 Bein in supergravity. And this is an E7 Lie group element, which we get by taking a linear combination of the E7 generators and exponentiating that. Now this 56 by 56 matrix then is decomposed into 4 28 by 28 blocks. These are these U and V matrices shown below. Well, matrices, yes, but we are then splitting the 28 index into 2 indices with range 8, and therefore we see them as 4 index quantities here. Then the line above this VAB introduces the so-called T-tensor. There are also other more modern ways to think about this thing, but nominally here in 4-dimensional supergravity, it's a 3rd-degree polynomial, and the matrix entries of the E7 group element, sorry. Now, taking this T-tensor, we can split it into irreducible representations, which then give us the U-cover couplings that tell us how the fermions and the Higgs fields couple. So from the A1 tensor, we can read off the gravitino masses, and A2 then gives the couplings between the gravitinos and spin 1/2 fermions. Sorry. So the scalar potential, the line at the top, is then a quadratic function of these two tensors that we see inside this T-tensor. Now, why are these supergravity vacua relevant? They're especially interesting for the ADS-CFT correspondence. So if we have a field theory where we think we have a good M-theory embedding, we have reason to believe that ADS-CFT should actually work. And having such examples allows us to make progress towards understanding CFTs and then also strongly coupled quantum field theories. So this is one of the objectives here. Also specifically in 4 dimensions, ADS4 we can see as the near horizon arising in the near horizon geometry of a stack of M2 branes. This is basically what BLG ABJM theory gives us. So by studying this, we learn something about a fundamental object of 11-dimensional M theory, the M2 brane. Then, of course, this construction is also relevant in other dimensions. If we look at the original Maldacena paper on ADS-CFT, this was about 2B superstring theory, the supergravity limit of that, compactified on a 5-sphere, which gives us 5-dimensional supergravity being equivalent to n equals 4 super Young-Mills theory. And here, the object that's relevant is the D3 branes. We are looking at the near horizon geometry of a stack of D3 branes. And of course, there's this cosmology question in the background, the phenomenological question whether M theory does have vacua at all that look somewhat like our world, and how one might obtain these. So now here are the known vacua of the de Witt-Nicolai model, SO8 supergravity again in 4 dimensions. Well, there is the vacuum with unbroken SO8 symmetry that has full supersymmetry, and this is known since the construction of the model. Then Nicholas Warner in 1983, using his group theoretic method, found two further vacua, one of them breaking SO8 to the exceptional group G2, and this has n equals 1 supersymmetry, and the other one with n equals 2 supersymmetry, breaking SO8 down to, funny enough, a gauge group, which is the same as the unbroken gauge group in the standard model. There's another solution from that period, which breaks SO8 to SO3 cross SO3 symmetry, doesn't have any supersymmetry, and there was quite some drama about this one. So discovered in 1982, it was thought for a long time that this actually would be unstable. And in 2009, when we actually then worked out the Higgs mass spectrum, we found that actually in that particular truncation, you do not see an instability. It looks as if it were perturbatively stable. But then a year ago, it was shown via two different methods that in fact there's an instability that just doesn't show in the supergravity truncation. Now in 2009, using hand backpropagated numerical code, I managed to find first numerical evidence for another vacuum with n equals 1 symmetry, and this was then confirmed analytically. And then in our 2019 paper, we found what we think is the final solution, another n equals 1 vacuum with residual symmetry SO3. And in that paper, we also give reasons why we think that this now is the complete list of vacua. In total, there are almost 200 perturbatively unstable equilibria in this model, but some of them are nevertheless interesting for other reasons. So here's a nice byproduct of these investigations. We found that about a quarter of all these equilibria, and in particular all the vacua, so in total 48 equilibria, sit on a particular 14-dimensional subspace of the scalar manifold. And on that particular space, you can obtain the scalar potential from an auxiliary quantity, which we call the holomorphic superpotential, that can be written in 7 complex coordinates. And the terms in this holomorphic superpotential, it's a polynomial, do precisely match the code words in the 743 1-bit error correcting Hamming code. Now, if we did the same game with maximal gauge 2 plus 1-dimensional supergravity, then we can do a similar construction and we get a superpotential that matches the self-dual 844 Hamming code, which nicely corresponds to the self-dual E8 lattice. And in fact, if we take the E8 lattice in a suitable definition and take all coordinates modulo Z2, we do get the 844 Hamming code. The coset manifold for that supergravity then is maximal non-compact form of E8, modding out the maximal compact subgroup. So how do we find these solutions? The basic strategy is that, well, we have this condition that all components of the gradient of the scalar potential need to be 0. This is what gives us the critical points. We've seen that the complication here is that the scalar potential is a complicated tensor algebraic polynomial in the matrix entries of an E7 group element. So we either need some parameterization of E7, such as via matrix exponential, or perhaps another algebraic condition. And we can embed E7 into SP56. And so we would need an extra condition that tells us that this particular SP56 element then is an E7 element. But really the point here is that we can do this algebraically. So we have an algebraic problem that is fully expressible in terms of tensorial invariance and integer coefficients. So all the relevant properties of a solution, such as particle masses, are actually algebraic numbers. Now, this allows us to use numerical optimization to fish for solutions, study properties, and then use numerical guidance to construct the fully algebraic form. This is what it looks like when all this works nicely. So this is a fully auto-generated solution, an unstable one, but as I said, we know all the stable vacua. So in the top row here, we see the symmetry breaking. SO8 gets broken to U1, well, to a subgroup of U1 cross U1. We have the vacuum energy density, the cosmological constant. We know this algebraically, so we know the polynomial of which this number is a root. Then we also know in detail how specifically U1 cross U1 is embedded in E8 and how the branching rules look like. And we get all the masses of the fermions and scalars and, well, also of course the gravitinos. I'm not showing the vector masses here, and I'm only giving these masses numerically, but we could work them out algebraically. We could work out the algebraic expressions here. And at the bottom, we have the location, the coordinates of that solution. Now, as I said, these solutions are algebraic in nature, but sometimes the algebraic complexity may well be out of reach. So we invested the effort to work out the minimal polynomials for the coordinates of one particular solution in detail using the PSLQ algorithm. And here this likely is the most complicated problem that ever was tackled with the PSLQ algorithm. So this is quite monstrous. You find it in one of the papers I listed earlier. We do think that for quite a few other solutions, we might not be able to ever get the algebraic form because of its complexity. And so numerics is the best we can do in these cases. So overall, life is not quite so easy with this problem due to a few complications. The first one is that the equilibria, even the vacua here, are in general not minima of the scalar potential, but saddle points. And there's a subtlety here. Normally, you would say that a stable solution would have to be an energy minimum, but due to the negative cosmological constant, that is ADS geometry, it's a bit more involved. And looking at the Hessian of the scalar potential written in such a way that we have proper normalization of the kinetic term. The condition for perturbative stability is that the eigenvalues of this Hessian, which are the squared masses of the Higgs bosons, if you want so, must all be above a bound, the Brighton-Lohner-Friedman bound, which is negative dimension minus 1 squared over 4, expressed in ADS units, masses expressed in ADS units. So this is generally a nuisance here. Now, if we just start from random points on the scalar manifold and fish for solutions by optimizing with these starting points, we might catch different solutions with very, very uneven likelihood. And we did develop some advanced numerical methods to partially counteract this. So in total, there are perhaps about, I would say, something like 40 different supergravities one would want to study that way. And another prominent modern example in 4 dimensions is the so-called dionic ISO 7 gauging, which one can get from massive Romans to A in 10 dimensions by compactifying that. So the current story there is that if this hypothesis is correct, that non-supersymmetric ADS solutions are all unstable, then again, we have examples where we cannot show this with current mathematical methods. There's a recent paper by Henning Sandleben and collaborators about this. So overall, where would I like to take this, and what's the thing that I cannot do alone? Personally, I'm seeing this problem of finding supergravity equilibria also as a nice sandbox for developing new numerical methods. To give one small example, if we want to do an automated study of the neighborhood of a local minimum, we can use the following structure. First, we locate the minimum. Then we introduce coordinates that bring the Hessian there to Sylvester normal form. And then we look at rays with random direction going outward from that minimum. And we iteratively start minimization increasingly far out along each such ray. And we check how far we can go out before minimization lands in a neighboring optimum. And the beauty of this method is that due to bringing the Hessian to Sylvester normal form, numerical optimization, in particular when we are using BFGS, is very fast as long as the third and higher order terms are small. So the diagonalization helps a lot here with the computation. So the question I would like to pose is whether we can evolve this strategy into a tool that can auto-generate proofs of the form. Well, we have this complicated function, and here are all the minima, demonstrably all the minima of this function of many parameters. So the first step for such a program, I think, would be to evolve it into something that can give us checksums, which can detect if we missed some solutions. So this basically would work by employing Morse theory. If we have a scalar function as they arise in supergravity, we would first have to slightly deform the scalar function, to slightly tilt it to break all the residual symmetry. In supergravity, we have a lot of residual symmetry typically. Then we can introduce an auxiliary function, which is the length squared of the gradient of this tilted function, and numerically determine its stationary points, fishing for them, and also doing this neighborhood analysis. And backpropagation tells us that we can do this about as easily as finding minima of the original function. So if we have this, and also if the problem is such that we can determine a maximum radius beyond which this length squared of the gradient just grows, we can cut off the graph at that radius. And this pruned graph we then can cap off with a ball to form a sphere. And well, at that point, we immediately know the Euler characteristic of that sphere, 0 in odd dimensions, 2 in even dimensions. And we can also compute the Euler characteristic via the Morse index of our critical points. So if these numbers match, if basically summing Morse indices over the critical points, if this way we reproduce the Euler characteristic, unfortunately, we don't really learn much. But if there's a mismatch, then we do know that we must still have missed one or more critical points. And I've done this, and this turned out to work actually quite well for a problem like finding the O4 model renormalization group fixed points. So the next step, I think, is to look into whether we can perhaps fully automate an approach that works as follows. We start from a Morse function. We then see if we can automatically work out a CW complex. So basically the composition of our space into cells that are disks. And then the question is whether we can use machine learning methods to auto-generate strict per cell bounds and near the minima also bounded models of the function. And this would then give us an automatic exhaustiveness proof. So we would, of course, not expect this to work well universally for the entire class of such problems, but it might be for some problems a nice complementary approach that is complementary to what already exists, which is homotopic continuation methods that are only algebraic in nature. So some potentially useful ingredients, if one wanted to do this, would be nonlinear transform coding, also rate distortion theory. This is something that colleagues of mine at Google and Research developed and recently published a paper about in the context of image compression. So this was done by and others this year. Then another ingredient I'm seeing here is affine arithmetic by Comber and Stolfi to get stringent boundedness proofs from numerics alone. And then perhaps in order to parameterize diffeomorphisms, potentially the matrix exponential might be a more well-behaved higher dimensional nonlinearity than what we normally build using deep neural network architectures. So this overall might be ambitious, but potentially it might be coming within reach here. And a toy problem I would propose to perhaps try to study that way would be the Thompson problem, specifically for 8-point charges on the surface of a 3D unit ball. So placing 8 electrons on the unit sphere gives a minimal energy configuration that is not the corners of the cube, but you can further lower the energy by rotating the top of the cube by 45 degrees and then relaxing it all. Still, this is a fully algebraic problem here. And in fact, thanks to the PSLQ algorithm, we think we know the energy for the minimal energy configuration. We just don't have a proof that this really is the minimum. Overall, this problem of the eliminating symmetry has 13 parameters. And the question here is whether we can machine synthesize a proof of minimality using the strategy I just outlined. So to conclude, some of the technology that we built at Google is useful quite well beyond the initial motivation that sparked its development, which here is machine learning. And we at Google Research are generally quite approachable about these things. So do feel free to reach out to us we do put our email addresses into our papers. And if you want to do something amazing with TensorFlow or perhaps the JAX library or some similar such technology, do come and talk to us. And with this, I'm concluding and I'm open for questions.
Very good. Thank you. Nikolai, you're clapping. Are other questions from the audience? I mean, that is quite an ambitious program to prove the exhaustiveness of the solutions.
Well, at Google Research, we like to be ambitious, as you've seen.
Right. So the way you described it was using, I mean, treating it as a relatively unstructured problem. And I guess we must know a lot about the space, the symmetries, the function, the problem of the potential has a lot of structure. But I guess it's not totally obvious how to use it.
Well, I mean, there are quite a few problems where the structure is not that difficult to understand. So coming back to this particular Hamming code superpotential,
Right.
the nice thing for this subproblem is that all the equilibria are actually isolated. So we can always move along the SO8 orbit to turn a solution into an equivalent solution by moving along the Goldstone directions. But the SO8 is perpendicular to this particular manifold. So that means that all the SO8, the orbits are perpendicular. That means that they intersect this manifold in isolated points. And this, I mean, if we could pull this off for the 48 different types of solutions. Actually, there are more solutions because each one on this 14-dimensional manifold, you see each of them multiple times, just having the coordinates permuted. So in total, you might get, I don't know, maybe something like 500 or 1,000 solutions. So if we could do that and show that really these 48 solutions are exhaustive, that would be pretty amazing to do. For the 3-dimensional problem, I know, well, I think I have seen 70 different critical points there, some of them quite interesting. And again, this is a 16-parameter problem. It would be really nice to be able to do something about that. And right now, I'm still somewhat optimistic, even though it's, as you say, challenging.
Yeah. More questions from the audience? Well, I mean, I have more questions, but I think they would take a while even to, it would be trying to talk about more general compactification manifolds and perhaps more general geometric questions. So perhaps we can find another time to do that.
Yeah, I'm very happy to have another chat about that specifically. And then we also can go a bit more into technical aspects. I mean, here the objective really was to give a high-level overview, and we would have to get more technical about that.
Very good, yes. So one point that you went over very quickly is as you say, you're not just looking for minima, and so you looked for, you used the square, the gradient as this, to find minima of that, to find critical points, and so you say that really doesn't cost anything. I mean, you might as well.
The insight here is that the length squared of the gradient is just a scalar, right? So we have that situation where we have many input parameters and we compute a scalar from it. And we know that working out this length squared of the gradient is at most 6 times the computational effort as it is to compute, in this case, the scalar potential, right?
Yeah.
And then taking the gradient of the length squared of the gradient only gives us another factor 6.
Right.
Working out a Hessian, however, well, normally you would say this would be order n squared effort. I can only break that down to order 6 times n effort. Unfortunately, I cannot make this just 36 times the effort, but this already as well is quite substantial. but basically you can also play this game to higher order, and I've actually done things with this where I've gone to some function of a matrix exponential of, well, an E7 or even E8 algebra element, and then taking well, a scalar function that ultimately involves taking a fourth, in one case even a fifth derivative, and that works. You can do that. So, well, the fifth derivative problem that actually turned out to be somewhat challenging, and this I then gave to our TensorFlow team as a stress test for TensorFlow. So this builds an internal graph that is a few gigabytes in size, and normally machine learning computational graphs are not that complicated. So this really then allows us to test the limits of what we've built.
Right. More questions? This is sort of a random tangential question, but I imagine people thought about this. If you compactify 11-dimensional supergravity on an exotic 7 sphere, does that make sense?
As far as I know, there's only a little bit of literature about that. I remember 2 papers about this that have not been cited widely. I've looked into them. I've read them. Well, I haven't checked whether it was done correctly.
But it's not evident nonsense. They do admit spinners, and it makes sense.
I think you can study this.
Do you know, or okay.
So
okay.
I wondered for some time whether this actually, and the answer is no, by the way, whether this actually might be related to this observation that you can do a weird deformation of 4-dimensional supergravity. So it was thought for a long time that this would be unique, but it isn't. There is one extra angle parameter with which you can deform it. And if you well, do that deformation, then there's no way to uplift this to 11 dimensions anymore, or rather no.
What is this deformation? I mean, can you say any more? Or do you...
This is this dionic rotation. So basically, you switch on magnetic couplings. One way to think about this is as follows. So if you look at E7, then this contains SU8, right? But it doesn't contain U8. And if you think in terms of electric magnetic duality, then you would use the U1 that extends this SU8 to U8 to do the electric magnetic rotation. That's actually not part of E7. And if you rotate the theory in such a way, then you're actually changing the scalar potential. And what you do get still, well, it is a kind of a valid construction. So when the systematics of 3-dimensional supergravity was worked out, Hermann Nicolai and Henning Samtleben found an alternative approach to understanding what goes and what doesn't in terms of a group theory argument, in terms of the so-called theta tensor, which describes the gauge group embedding. And then Henning Samtleben with Bernard de Witt systematized this and wrote it up, what this then means for high dimensional supergravity, so in particular 4 and 5 dimensions, I think around 2007 or so. And you can show that this alternative construction satisfies the theta tensor conditions. So it is a valid construction of a supergravity. It satisfies all the gaugeability conditions, but it's not obtainable by an uplift. Interestingly, also the 3-dimensional maximal gauged supergravities, 32 supercharges, you cannot get in any known way from 11-dimensional supergravity. You cannot uplift those. But there seems to be a kind of explanation of this dionic rotation if you look at the 3-dimensional potential supergravity. So you can actually interpret it as the U1 rotation that sits inside the SL2, which you get from embedding E7 cross SL2 into E8. So non-compact forms of these groups. So there's numerical evidence that this really works. And I put a short note about this on arXiv that also links to a Colab that you can run directly in your browser. So a Google Colab notebook that shows how the mathematics works there, how the construction works.
Okay, thanks. Okay, well, if there are no further questions, well, let's thank Thomas for an enlightening talk. And next week, we'll have Marijn Hoyle from CMU to talk about using SAT solving to solve combinatorial and mathematical problems. So I hope to see you all there next week. Thanks.
See you.
Okay. I'll write it later about perhaps meeting talks.
Maybe we'll set up some other meeting.
Okay.